Awesome.
It's supposed to be a surprise.
Greetings and welcome, friends.
Just you.
Friends of all ages, permutations with repetition and circular perms. That's right, I just called it like permutations. And actually the coolest thing about this title is that this title has repetition within it because it started with permutations and it ended with permutations. How crazy is that? So I'm going to just jump right into this example, which is at the crux of the matter today. It says, how many ways can we arrange the letters in the word book?
Oh, I thought you meant like the word book, and I'm like, what's the word book?
What's the word book?
You should have put it
I was like, you mean the dictionary?
quotations over it.
Yeah, I could see that. I'll throw in some like little
The word,
whoop,
comma, book.
whoop, whoop. There we go. That's the best I can do. So one arrangement, I think you would agree, is B-O-O-K. Bouquet is how that's spelled. Another arrangement would be like Boko, right? And then another one would be like B-K-O-O, right? And then there'd be like more. And then, oh, yeah, Koob, Stanley Kubrick. Yep. And
Ubu.
Akbo and Ukub.
I feel like we should start a little German like brain now.
Yeah, we should actually.
Wow, yeah. I think Akbo would be a great like name brand for boots, I'm thinking. So anyways, but eventually I come to the point, well, what about book, where I switched the O's?
No, but that's stupid.
And you might be like, well, that's somewhat indistinguishable from the t'other one, right? I think you would agree that book and book kind of look the same because there's no distinguishing factor between those, right? Like if you're playing Scrabble and you're like, I'm going to play the word book, and then they're like, oh, book, that's this many points. You're like, no, I was playing book where the O's were the other way than the way you thought I had them played, right? That wouldn't... Exactly. So, like, they're indistinguishable. What would the point be of trying to claim that these are two different things? So, I'd want to find a way of getting rid of that repetition, right? Just like how Boko, oh, I could also have Boko where I switched the O's there. So, in order to figure this out, this is how we think about it. First of all, how many ways could I just arrange, Jacob and Kirsten, how many ways could I arrange just plain old 4 letters book? How many ways could I arrange it just total? 4 factorial, or Hank's got it, 24, right? All right. You could have also thought about that as like permutation 4-4, but we'll just call that 4 factorial, 4 facti, right? And now question, how many ways could I arrange 2 letters, specifically the 2 O's? How many ways can I arrange 2 letters?
2.
That'd be permutation 2-2 or 2 factorial. And if I divide these 2 things,
2 permutations.
I'm going to eliminate the repetition of all of these as a result. So I'm going to have 4 times 3 times 2 facti over 2 facti. And I'd have those 2 factis cancel like so. And I have 4 times 3, which is 12 ways. Actually, yeah, it took me a little while to find them all myself.
Why couldn't you just simplify it and be like, no, this doesn't make sense.
What are you saying? Yep.
Like, cross out the 2.
So you're saying that 4 factorial divided by 2 factorial should be 2 factorial?
Yeah.
Aha, I think we found the error in your reasoning. Because 2 factorial would mean 2 times 1, which I think you would agree is different than 4 times 3.
No,
So you can't cancel out factorial fractions like that. Good question. Wow, I never thought to bring that up. So good call.
Why is it different? You just have to assume that it's wrong.
Well, now we know that it's wrong. So here are my 12 actual arrangements. It looks like I had 3 that started with B, 6 that started with O, and 3 that started with K. And that's what we've got, 12 total. I figured I'd throw those in there because you wouldn't just want to believe me that there was 12.
And now I have them all. I'm
Right.
missing one.
Yeah, you caught Mewtwo. Congratulations. So I think you'd agree that listing them all out would not be effective if I had, say, 13 things being arranged with a couple that were repeated, right? That in those cases, you'd want to be able to rely on some sort of formulaic approach instead of having to literally make a list of so many things, blah, 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 blah. So let me give you a handy-dandy formuloni. Ravioli, ravioli, give me the formuloni. So, so permutations with repetition. Repetitions, repetitions. There we go. So if there are n objects, p are alike and q are alike, the number of permutations is n factorial divided by p factorial, q factorial. So basically I just divide by the number of reps that occur. And let's say like there was another thing in the list that was repeated, then I would divide by like r factorial or s factorial. And I just keep dividing by the number of things that were repeated, factorialize it, and I'm good. I'm good. So, that is the general concept for permutations with repetitions. And let's do the classic example that no math class talking about permutations with repetitions could be without. How many ways could we arrange the letters in the word Mississippi? I believe that's how it's pronounced. I have no idea. Actually, I've got a friend from Mississippi. I should ask him. So I'm going to use this little pattern formula, I almost said, right there. So first of all, how many letters are there in the word Mississippi? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep. So that is 1 Mississippi, 2 Mississippi. So 11 factorial is the number of letters. Now, how many? Let's consider repetitions. How many I's are there, or how many M's are there? 1. How many I's are there? 4. So I'm going to divide by a 4 factorial. Let's see. How many S's are there?
4.
Also 4 of them. Isn't that special? Divide by another factorial. And how many, let's see, I've got the I's, I've got the S's, I've got the I's.
2 P's. 2 P's.
2 P's. So I'm going to divide by 2 factorial. So my answer is just going to be a matter of simplifying this. So I'll actually write this out the long way. 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. All over 4 factorial. That'll cancel out nicely. The other 4 factorial I'll have to write out 4 times 3 times 2. And then the other 2 factorial I'll just write as 2. So watch my Fruit Ninja skills on this. Let's see how good I can pair things up to eliminate them. Let's see, the 4 facties cancel out. Let's see. Oh, I see a 3 times 2. That's 6. And 4 and 2, that would cancel out nicely with my 8 up here. So it looks like my answer would just come from the 11 times 10, 11sies times 10 times 9 times 7 times 5.
Why?
Why what?
Wait. Why are you not putting, because 4 crossing out with the 8 is 2, not nothing.
Well, I canceled out this 4 and this 2 with an 8. So yeah, I mean,
Oh, okay.
yeah, so you can cancel out a whole bunch of different ways. I like that game. I think I need to make an app called Cancel Out, where you just have like fractions of things.
There's this crazy math app that's like number one in the market right now. And it's just like, listen, you have to like try to get all like.
Oh, is it threes?
No.
Okay.
All the tiles like add up to this one number, and then you have to get out of the puzzle
Also,
without touching new numbers. You guys have the number. Like,
speaking of apps, the other day you were talking about the game Set and the number of ways that sets could match. I did find an app called Triple or Triples on Android. There's actually, if you go to the wiki page for Set, the game, it'll have a bunch of links down at the bottom of different apps that are essentially that game. Sadly, none of them have multiplayer. Very sad deficiency.
I'm calling 12 on this one.
Hank, you know it.
So guys, check this out. I've got a circular table. Not a circular table saw, please. And I've got 4 people. So I've got like person 1 and person 2 and person 3 and person 4. And the question is, how many ways can 4 people sit at a circular table? Oh, so you're viewing like having person 1 sit at like the infinitely many degree possibilities. No, we're talking just like person 1 is sitting next to person 4 and person 2.
They should just sit at a square table.
Yeah, why is that circular?
Well, circular tables exist. We have one in our room if you can't imagine it well enough by this awesome picture that I drew. But the point is that you might be like, oh, that's just going to be 4 factorial ways, right? P4, 4. However, consider the following. 1, 2, 3, 4, I could have rearranged that as 4, 1, 2, 3. What's the difference between these two? Yeah, it's just rotated like so. And I think you agree I could rotate again and I could have 3, 4, 1, 2, or 2, 3, 4, 1. And those are all just rotations of the same thing. So I actually have to eliminate those possible rotations, which is actually dividing by, there are 4 possible rotations because there were 4 positions, so to speak, to sit at the table. And I agree that technically you're right, you could have people sitting at different, like, 1 and 4, maybe they're all getting buddy-buddy and sitting real close to each other. And I agree that's technically different. But with respect to this problem, it's who's sitting next to who, or should I say whom? Perhaps. But 4 factorial over 4, which by the way is 4 times 3 times 2 times 1. Hey, I wrote the 1 that time. Which notice, wait a minute. This is how many ways? 6 ways. And so there are 6 ways for this to occur. And if we wanted, we could even do like a lab activity where I have 4 of you go try to sit at that round table.
Okay.
And then you'd write like a lab report about the number of possible ways it worked out. And it would be wonderful, like you would have had a hypothesis and a conclusion. But I don't think that would actually be that helpful for us. Also notice this little guy right here, 3 times 2 times 1. I also could have perceived that as being 3 factorial. Am I right?
Are you saying that labs aren't helpful?
Oh, no, I'm
I
not.
think that's right. Which means this forensics curriculum is all wrong.
I'm just saying that in this case, this problem was more easily approached using other techniques. So, circular permutation situation right here. If there are n objects arranged in a circle, the number of permutations is n factorial over n. Or, you could also use the formula n minus 1 factorial. Both of these formulas are equivalently good.
What's your song after you're done
I want to listen to it.
N times n minus 1 times n minus 2. You don't have to write this part down. But if I wrote what n factorial meant, let's say it looked something like this, and put that over n, notice that the n's could cancel out, and I'd be left with something that is equivalent to just n minus 1 factorial. So that's why the second part of the formula is there. It's just a simplified version if you want to think about it that way. And also, it would be super illegal to try to distribute a factorial over parentheses. Yeah, don't do that. Don't do that. So, circular permutations.
Is that it?
Well, I've got a couple little more things to consider. So,
I didn't finish writing that
What you know
down.
about me?
I will come back to it at the end, Van. It'll be fine. It'll be fine. So, let's draw a picture of this. How many ways can I arrange 6 beads on a bracelet with no clasp? Also notice that there's no implication that there's any repetition amongst those beads. So let's say I've got like beads, 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 beads. I'm running out of shapes, guys. Oh, maybe I could draw like a house-looking bead.
Diamond. Oh,
Diamond.
Just a
Oval. How about trapezoid?
That's stupid.
Because I already had a parallelogram. Let's see, 1, 2. So 1, 2, 3, 4, 5, 6. So I've got 6 beads arranged on a bracelet with no visible clasp. All right. So it's like an infinite bracelet, so to speak. Now you might be like, oh, so that's 6 objects. Oh, but it's circular because I could rotate and rotate again and rotate, and there'd be like I'd have to get rid of all those things, right? So you'd be like 6 factorial over 6 if you're viewing this as a circular permutation problem. Now, however, what if I showed you this?
ABC.
It's easy as 1, 2, 3, A. Yeah,
I agree these are the same exact bracelet, except what happened?
you rotated them.
It was flipped over.
Whoa.
Right? Because like just like your car keys or a bracelet, it could sit on a flat surface flipped over, and that's going to eliminate half of my possibilities. So I'm going to have another 2 in the denominator
Why?
Yeah, why?
to account for the flipping.
Well, what if the table flipped over?
And that's exactly what I'd wanted to bring up, is why didn't we consider this flipping over with a table? Because we don't want to make people sit on their heads, and if anyone's flipping tables over, it's Jesus in the temple. What? Oh man, craziness. I'm sorry. Anyways, so 6 times 5 times 4 times 3 times 2. All over 6 times 2. And let's cancel out the 6 and the 6 and the 2 and the 2. And I've got 5 times 4 is 20 times 3. Looks like 60 possible combinations or ways that this bracelet could be arranged with no clasp.
I thought I said no.
It doesn't make any sense.
No? Well, don't you agree that like flipping over, it's really exactly the same bracelet? Someone just came over and like flipped it over on a desk or something. And now this last example is very similar, except it's got one unique outcome as a result. So Kirsten, imagine a bracelet again with 6 beads, but with a clasp.
One way.
So imagine I've got a clasp, right? And then I've got my like bracelet thing.
Literally,
Do a noodle.
Or peanut. Wait, so you're allowed to flip it upside down?
What is that?
That's a noodle.
I'm trying to draw like elbow macaroni,
Yeah.
but it was sad.
Peanut.
Do a peanut.
Peanut noodle.
Ah.
Peanut.
Take it left.
So, behold, how many ways can I arrange 6 beads on a bracelet with a clasp? Now, consider this. this can be arranged in a circle, right? I put this clasp through here. It's like a straight up bracelet. And you could flip it and you could do all that. However, consider the following. This bracelet could be arranged or viewed this way.
OMG.
Oh.
Mind blown, am I right?
I really don't even understand what you just did. That's like,
All right, it's like I unclasped the bracelet and I stretched it out, and it's no longer a circular permutation problem. This thing is straight up linear. Straight up linear. Get like, there's like play on words there almost. Yeah, it's horizontal, you're right. So, how do I arrange 6 objects in a row? That's just plain old perm 6, 6, or 6 factorial, whichever way you want to think about it.
Oh.
What is 6 factorial?
Stop.
I don't remember.
I know.
I know what it is.
Do it in
I know 5 factorial.
Do it in your head. 6 times 5.
Yeah, you're right. So because of the existence of a clasp or something that can distinguish my circular arrangement from other possibilities, it's actually a linear setup, even though it happens to look like it's a circle at the time. Other problems that will come up this way will be like, how many ways can people sit at a round table if there's a microphone in front of one of the chairs? And it's like, okay, there's something that distinguishes that point, so I could view this as a linear arrangement, right? Or how many ways could people sit around a campfire if only, I don't know, there's like a poking stick at one of the seats or what, like, I don't know. Who knows, right? So that's the general idea. So today's lesson, Willow and Caitlin, was about permutations and what we do to deal with repetition, represent their circular nature at times and how to eliminate those duplicates, and how to eliminate flippability, so to speak, and then how to not fall for when there's a linear problem in disguise as a circular. Thanks for watching, friends. Adios.